Yeah, so this section, we're talking about limits of functions and the limit laws. So basically what we're going to start off by getting an informal definition of a limit, because the formal definition will come next section. We're going to do the epsilon delta proofs, and as epsilon gets closer to L. But today we're just going to look at the basic concepts of what it's all about. And then we're going to define the laws of limits. What are the parameters that we could deal with? The limit of function values. What we're talking about here are whenever we talk about limits and functions, there's a condition that we have to have. The function has to be continuous. On an interval. Because, as I said, in order for us to be able to talk about this stuff, we have to know that each point of the function is defined. And that's what continuity is all about. And again, we're going to define continuity later on. What we're going to look at is we will examine the values of the function as x approaches some value c. But not at c itself. There you have the first conditions that we have to look at. When we talk about limits, okay, well, so let's first see what we're talking about here. We have a function, f of x. What is the c value? What is the c value we're talking about?
It's the that's basically the limiting value.
Well, yes, it's the value. In essence, we're looking at even any function. It's if it's undefined at a certain value, that's our c. C has to be within that domain also. And so what we're looking for is the quotient function that's a different question. It was delta y over delta x, which we looked at the other day as delta y over h. When we talk about the quotient function, that's what we're looking at. The whole object is we're trying to find the rate of change, the slope of a curve at a given point. That's what the point is at C. That's what we're looking at. So if we looked at a graph, any function, we have x1 here, we have x2 here. F of x1 there, and f of x2 there. Now remember, this is the same thing as y1, this is the same thing as y2. If we find the slope of these 2 points here, point 1 and point 2, what are we finding? If we connect both of those points, right, we're finding the slope of the secant line. Because that's 2 points on a curve. So the tangent line, I mean, the slope line, equation line, crosses the curve at 2 points. That's what a secant is. What we're looking for is the instantaneous slope at a given point. So what we have here is this. The distance between x1 and x2 is called h. Because how would we get from x1 to x2? x1, if we add h to it, then we get to x2. Now, if we subtract x1 from both sides, then h is equal to x2 minus x1, which is what we have here, x2 minus x1. And the change of y is fx2 minus fx1. But because of this, remember, we're trying to get down to only 1 point. So the only point we want is x. What's happening is, as h, the distance here goes to 0. What is that going to mean? It means that x2 moves closer and closer and closer to x1. Eventually, h will become 0. The distance between them becomes 0. And when we do that, what we're going to end up with is the slope of the tangent line at 1 point. That is our ultimate goal.
The closer, or the lower the value of h gets, the more accurate the slope.
Well, yeah, the closer we get to the tangent line. So what happens here is, as x2 gets closer to x1, f of x2 approaches, it gets lower and lower and lower to here, because the points get closer and closer and closer. And that's what we call our limit point. Wherever we end up at, that's what we call our limit point. So we're going to pick a point C, anywhere between in the interval, and we're going to look for a value L. That is our ultimate goal, what we're looking for. So let's look at an example. So remember, the delta x has to get close to 0. Delta y has to get close to 0. So eventually what we want is both of those terms become infinitely close to 0. So it tells us what we're heading towards, what our values are. So here's our first example. Here's our first example. How does the function f of x equal delta y over delta x equal x squared minus 1, x minus 1 behave when it gets near 1? What happens to the function as it gets closer to 1?
It goes closer to, or, well, as it becomes, as it here, I see. That means that it can be below 1 greater.
Well, let's see what happens here. Actually, that does find something. 0 over 0 is a valid function. But whenever you get 0 over 0, that tells us something in algebra. What does it tell us? If at a value, if we put x equals 1 in here and it gets 0 over 0, that means that they both have something in common. It's not intercept. It's actually it's going to be an asymptote because the bottom is 0. So what do we do?
So we put in. It's the bottom. Back with the top. Plus one.
Yeah, so we factor the function. So f of x now becomes, this is a difference of two squares, which is x plus 1, x minus 1 over the bottom x minus 1. Because what's happening here, because if we plug in 1, if x equals 1, we get 0 on the bottom. If we looked at a graph like this, it's a linear equation, but there's a hole there at 1. Because we can't use 1 because it'll become undefined. But if we get rid of those, this function at 1 now has a point. It equals 2. So our original function, x squared minus 1 over x minus 1, has a hole in it. But our updated fixed function, everything is defined. It's a continuous function now. So what we're looking for here, we know that this is going to be our answer we're looking for because of this. We should get the same thing here. If we look at all the numbers bigger than 1 that are getting smaller and closer to 1, these values are all going to get closer to 2 from the top. Likewise, if we do it from the bottom, these values, the graph gets higher. Eventually, it's going to 2. It doesn't have to get there, but it just has to approach the same value from both sides. Let me show you what that means. Here's our function, x squared minus 1 over x minus 1. This side of the equation is going in from the bottom, from 0 to 0.9. Okay, I was skipping everything from 0 to 0.9. That's getting closer. Let's look at from 0.9. How close is it getting? At 0.9, we get 1.9. At 0.99, here's my x values. At 0.99, make it bigger. We get 1.99. As we get closer, we're getting to a limit point. It's getting each step. We get closer to 1. This is getting closer to 2. Now from the other side, from 1.1, let's go down. We're going from 1.1, we're getting closer, we're going to go down to 1.0. As this gets smaller and closer to 1, this gets closer to 2. So we know that our C value is 1. As it gets closer to 1, our Y values get closer to 2. That's our limit. That's what we're trying to get to. That's what the whole thing's about. So let's define this thing now. Oops. I have to go back up to here. Remember, we're looking at an informal definition here. So, an informal definition or description of the limit of a function. Let's say that f of x is our function. It is defined on an open interval, AB. Except possibly at a value C. C is inside that open interval. If the function f of x gets infinitely close to a number L, L is the limit value, if x gets infinitely close to a number L, for every x in the interval, as x approaches the value C, we say that the function of f of x equals L. As x approaches C. Because remember, we're looking at a function, it gets arbitrarily close to a limit value for every x. Remember, C's are our arbitrary value. That's the limit value we're gonna look at. So when we plug in f of C, we get the limit. That has to exist for it to be continuous. But it doesn't have to exist for the limit to exist. Okay, so let me put that down. F of C equals some number, some limit number, has to exist to be continuous, but f of C doesn't have to actually equal L to have a limit. This is the way we would write our limit function. This is how we write our limit function. The limit of f of x as x approaches C, some specific value, then it equals L. This is read the limit of f of x as x approaches c equals some limit value L. That's how it's read. And we just abbreviate it saying that at the limit as x approaches c of f equals L. So look at our first example. Look at our first example. How would we write the limit on that one? Remember example one? We had f of x equals x squared minus 1 over x minus 1. We're looking at the value when x equals 1. This is our c value. Of f of x, right? What was the number we came up with? Well, remember, after we simplified it, what did it equal? 2. Because remember, after we fixed it, it was x plus 1, which equals 1 plus 1 equals 2. So this is how we would, this is how we'd see it in an equation. So the values of f of x are close to L, the limiting number, whenever x approaches c, or it's close to c. So basically, I'm gonna give you, I'm gonna spoil the game here pretty quick. Well, let's look at example 2. I'm gonna spoil it in a second. The limit of a function does not depend on how the function is defined at the point being approached. So in other words, again, it doesn't, for a limit to exist, it doesn't have to exist. It doesn't have to be a defined function. It just has to approach it from both directions. So consider the 3 functions below. What would be the limit of this first one? How about the second one? Put the dots down here. Because remember, we're coming from top and bottom. Where are these values approaching? Yeah, so it's not where the number is. It's where it's approaching from both sides. And this one's the easiest one. They all mean the same thing. So it doesn't matter whether it exists, because here at this point here, it's undefined. But here, it's still somewhere else. And again, the limit is where it's approaching. That's the hardest part for students to remember, is it doesn't have to be that point. It's just, it has to approach it, but it has to approach it from both sides. We're going to look at later on limits from one direction, because this works great if our interval was, let's say, from 0 to 5. one is between there, so we can approach the limit. But what if we're looking at a limit at a endpoint? We can't go the other direction. So that's a whole nother set of rules there. So for right now, we're looking at an open interval and we have a function inside there. This. Let's look at this one. Find the limit of the identity function and of a constant function. Do the limits exist there? Here's our C. This should be L because it approaches a limit. I don't see why they put C there. But as our points get closer to C, what happens to our points on the y-axis? Likewise here, as this one comes through. Oh, that's why they put C, because the function is y equals x. So if this is 4, that's 4. If I'm coming down closer to 4, my limit's going to be 4. In a constant function, that's even easier. If you have a horizontal line, it's always going to be the same value. Because as x gets closer to C here, it's always going to stay the same. So in that case, it's going to be, if you have a constant function, a horizontal line, 0 slope, then it's always, the limit's always that constant value. So if I gave you this function, if I gave you this, what's the answer? What's the limit? Yeah. Because no matter what x you give me, y is 6. It's always going to stay 6. But what this one's saying here is the limit of f of x as x approaches 0, or to say 8. Then the limit of that one is going to be what? 8. Because the function is the value. Yeah, so no work need to be done there. Sometimes it's just that simple. Let's see, let's give another example here. Oh, another example. Yes. This should be this is g of x equals, this is u of x equals, and this is f of x equals. Discuss the behavior of the function and explain why they have no limit as x approaches 0. If possible, draw the graph of the function. So this first one, go ahead and draw the graph of the first one, and let's see what it looks like. This is a mistake here. It should be 0. Let's look at A. Let's look at the first one. U of X is equal to 0 and 1. X is less than 0. Let's make that's what the mistake was. The bottom one should be greater than equal to 0. So what happens here? The first graph, for anything less than 0, the answer is 0. So it's this line here. And it has an open circle there. When X is greater than or equal to 0, it equals 1. So there's a solid dot, and it's a horizontal line that way. So what's the limit as X goes to 0? It's not that, but it doesn't have to be continuous. Remember that first example we had the hole in the middle? It's just that if I come from the right, what is it approaching? What value? If I come from the left, what is it approaching? Are they the same value? So it's not, there's both directions have to equal the same number. One over X when X is not equal to 0, and 0 when X equals 0. Let's go review algebra again. So when X equals 0, it's 0. The rational function, we can't have X equals 0 because it's undefined. What does the graph look like? When X equals 1, what does Y equal? It equals 1. When X equals 2, what does Y equal? Half. When X equals 10, and when X equals 1/2. Two. When X is 1/10 is 10. So it looks like this. Has a horizontal asymptote at 0 and has a vertical asymptote at 0. But when it's negative, same thing. Equals -1. When X is -2, that's 1/2. When X is -10, so it goes up this way. So what's the limit as X approaches 0? No, because if I come from the right, where is it going? Positive infinity. If I come from the left, it's going to infinity. So no limit. So if you have a jump discontinuity like this one, it's called a jump discontinuity, it doesn't have a limit. If you have your end behaviors going different direction, no limit. The last one, 0 when x is less than or equal to 0. I gotta change that too. And it's sine of 1 over x when x is greater than 0. So we know what the sine function looks like. At 0, it's 0. And it goes up to 1, -1, and continues like that. But when the angle is a rational angle, what happens here when x is less than or equal to 0, it's 0. So it's like this. But for the other side, when x is small, when x is less than 1, it grows up very big. So it grows really fast and it dampens the bigger it gets. Because the smaller this number becomes. So when this one approaches 0 from the left, it's approaching where? 0. When this one's approaching from the right, it's jumping up and down. This is called an oscillating function. It goes up and down, positive, negative, and we don't know where it's going.
That's all.
That's what,
Yeah.
well, yeah, it's, if you're trying to make it, well, if it's just a plain sine and cosine, we can tell at pi over 2, what's the limit going to be because it's approaching at that point. But when it's oscillating that non-harmonically, if we're going to infinity, notice since it's dampening, it's getting smaller, we know it's going towards 0. But towards 0, it's just getting very sporadic. So it's a no limit. So those are 3 examples of when limits don't exist. Let's look at the laws. This is also a theorem. The limit laws. There are about 7 or 8 of them. Before I continue, I have to define my limits. The limit as x approaches c of f of x is L. The limit as x approaches c of g of x, that equals m. Because I have to define what the limits are going towards. The limit as x approaches c of f of x plus g of x. Notice they're inside the parentheses. They're part of the same limit. We can split these up. The limit as x approaches c of f of x plus the limit as x approaches c of g of x. The limit of f of x equals L plus the limit of g of x equals m. There's the first one. So far, so good. Then the second rule. Let's go the opposite direction. The difference rule. the limit as x approaches c of f of x minus g of x. It becomes the limit as x approaches c of f of x minus the limit as x approaches c of g of x. So what's the limit of f of x? L. The limit of g of x is m. The constant multiple rule. The limit as x approaches c of some constant times f of x any constant that's not a function of x, I can put outside the limit. So it's the limit of f of x as x approaches c is L. So it's k times L. The product rule. Limit as x approaches c of f of x times g of x is the limit as x approaches c of f of x times the limit as x approaches c of g of x, which is L times M. Then we have the quotient. Oh, I'm sorry, you need back up there? Yeah, I mean, if I'm going too fast, just tell me. Yeah. I need to remember I was at 5. Number 5, the quotient rule. The limit as x approaches c of f of x divided by g of x equals the limit as x approaches c of f of x divided by the limit as x approaches c of g of x. This is L over M. M cannot equal 0. Neither can the limit of g of x can equal 0. The next one is the power rule. The limit as x approaches c of f of x raised to some power n is equal to L to the power n. And it's an integer. Powers, we go to the rational powers, the root rule. The limit as x approaches c of some nth root of some function is equal to the nth root of that limit of the function.
So you would take the root of the limit.
These two rules are the same because well, let's go back to algebra. Or m over n, sorry. So then we could just go back to the power rule, which is if we did that, then we would have the limit as x approaches c of f of x to the power 1 over n, which becomes n to that, which becomes, so it's just a roundabout way of doing it.
Right.
Let's look at some examples on these. Yeah, those are the 7 rules. The whole purpose of these is to take larger equations and make them into smaller pieces. What's that? But yeah, those are the laws. Those are the limit laws. Oh, logarithm. Yes, exactly. Exactly. Like when we had you take a logarithm and then I'm sorry. Yes, it's exactly a perfect example because you could take a complex function, a logarithmic function, and break it up into the sum and difference rules. Yes, that's exactly what it's a perfect example. All right. So use the observations k equals k and x equals c as the limit laws in the theorem to find the following limits. Uh-oh. Well, our limit is when x approaches c. So the limit as x approaches c of x cubed plus 4x squared minus 3. Which rule are you going to use? Yep. You can't use the power rule here because the whole thing's not raised to a power. So you would use the sum and difference rules. The first thing you would do is take the limit as x approaches c of the first one, plus the limit as x approaches c of the second one. Oh, yeah, of course. Oh, wow, that is a big difference. Wow. So now we can use all those sub rules, because in the one big equation, you can't use that one rule. You can't use the power rule, you can't use the quotient rule. You have to break them up first, like the logarithms.
So you're using a rule for each term of the polynomial,
Yes,
essentially.
because there are three terms, so we can split them up. We use the first rule of the product, the sum and difference, and then that makes it easier now to do smaller pieces.
Yeah,
So it'd be c to the 3 plus 4c squared minus 3. X to the 4th plus x squared minus 1 over x squared plus 5. So basically, I'm sorry, I put b up here. We find the limit as x approaches c.
so you use the sum and difference rule and then the quotient.
Not in that order.
Quotient.
Yeah, because you have to, what does the quotient rule tell us?
F of x over.
So in other words, pretty much what it tells us is this: we can treat both of these separately. So because we couldn't do it right here with the limit out in front. So we have to put those. Now we have the sum and different rules. X squared plus the limit. These are all supposed to have x goes to c in the bottom. Then what? Then put c for x. So we get c to the 4th plus c squared minus 1, c squared plus 5. Now we,
And
is there a rule that has a combination like that, a chain type rule? Let's look at rule number 7, the root rule. Does it say anything about f of x inside there being anything done to it other than just a limit to it? So what this one says is as x approaches c, we have 4x squared minus 3 to the power 1/2. There's our f of x. So what that one looks like then is 4c squared minus 3 to the power 1/2. Or you can leave it as a radical. Is there a shortcut to this? You say maybe? Yeah, it's true. It's either a yes or a no. Is there a faster way of doing this? Yeah, at the very beginning. The first line of defense in this thing is when you're given a limit function, plug C in there. If it gives you a number, you're finished. But if it gives you something that's undefined or 0/0, then you have to go another step further. But don't waste your time. Check it out first. You have a 50-50 chance.
Right.
So there's nothing to lose.
Because you replace that with variable C, then you're unless there is.
Right. Unless or it's undefined or yeah.
And then you have to just do a little bit of algebra.
Well, let's look at this. Let's look at these three. Let's say C is 1. Oh, let's do C is 0. Let's make it easier for us. Do these three as the limit goes to 0. Yeah, it'll be -3,
-1.5.
right? It'd be, it's imaginary. Right, so that's your first step. Go there. And since we've defined imaginary terms, we can use those. But we can't say we have a real answer, we have an imaginary answer.
And you have to explicitly state that. You say no real.
Well, the question has to state, if it just simply says solve or find the solution, then you say, okay, it's radical 3i. But if it doesn't say it's to find all real solutions, then you have to say there are no real solutions. Yeah, so again, it all depends on how the question is stated, because you have to answer what the question's asking. And that's a lot of times where people shoot themselves in the foot because
they answer a question.
they answer a question exactly. It's not necessarily what it wants,
Yeah.
and then you get all these red X's, but they got it all right, which is a drawback of electronic grading. I mean, I know what you're. If I kind of test, that's why I always ask students, give me a proof of work on your test. So just in case it got it wrong, or if you got it wrong, then I'll say, just send me your proof of work and I'll see.
Can we just submit our, like, to our line, for example, just screenshot, like, I usually do this on paper or.
Well, yeah, you should always do it on paper. Always do it on paper. It's your work. You're always, because that way you can always go back. If you think you got it right and it says you got it wrong, then send me the question and send me your work, and I'll see if it's wrong because it was in a different format.
Right.
Which again, that's a drawback. It's because if your answer was 3x to the 5th, and it wanted 3x to the -5, it's gonna count it wrong.
Right, even though they're equal.
They're the same thing.
Because it says it a lot on there. It says equal, but read this instructions, like I've gotten on this all the time, dude, but where it's like I'll answer out to, to 1,000 precision, and it wants it, a whole integer.
Yeah, or rounding up, yeah, or just truncated at 2 into, yeah. And so again, that's the drawback because but it's getting better. It's getting better at that. All right, the next topic. Evaluating limits. Of large polynomials and rational functions. We've actually did that. That's the topic, but we just did that in an example using the sum and difference rule for large polynomials. And then the rational functions, we separate them, the two into two separate equations. Theorem 2. Polynomial limits. or limits of polynomials. If P of X is some polynomial AX to the power N plus B, or let's say AN minus 1 X to the power N minus 1 plus AN minus 2 X N minus 2 all the way down to A1X plus A 0. That's an nth order polynomial. If you take the limit of that polynomial, just plug it in there. Isn't that what we just did? We just said, anywhere you see an X, put a C. Remember, it's not a derivative. It's the linear, it's the function itself. We're at a specific value. There's no derivative. So if you have a constant, you'll have a constant at the end. So what do we just do here? I just took it at the limit point. At X equals C. That's what I did there. Theorem 3 is the rational limits, or limits of rational functions. P of X and Q of X are polynomials. Where Q of X does not equal 0. So the limit of the rational function P of X over Q of X is simply equal to P of C over Q of C. What do? They just plugged in anywhere C and X, put a C, and if it works, it works. But these, if they work, they work. If they don't, then we have something else to work with. Here's an example. Take the limit as X approaches C of this polynomial, rational polynomial.
-3.
No.
Oh, yeah, C. I was thinking 0, I just put in 0 in there.
Okay, then let's put it with a value 1, since you already did 0. And so we have 1 squared plus 4 times 1 squared. 1. What's that?
Can you do that? You don't have to be a cube, 1 cube, not 4. 1
Oh, it's supposed to be yes. Is that new math? So 1 cubed is 1. 1 squared is 1 times 4 is 4. 1 plus 5. Right. What would happen if we went to -1? Mhm.
Negative 1 plus 4 minus 3. That's either.
Seems like you want those.
Because now it changes because since we have odd and even functions, our exponents. So -1 cubed becomes -1. -1 squared is 1 times 4, so plus 4. -1 squared is 1. -1 minus 3 is -4. So the limit is 0. It's not, it doesn't exist. It's 0. 0 is a value. Because in the past, I had a lot of students saying, okay, it's 0, so it doesn't exist. No, it is 0. It is 0.
Because it's not undefined.
Right.
Because it's only undefined if it's undefined.
If it was 6/0. But can we go any further with it? If it was 6/0,
You could, because then you would factor the numerator and the denominator.
that only works with 0/0
Oh, okay.
because they both have something in common. I mean, you could try something and see if anything works, but sometimes it's just undefined because we found that no limits exist on those first 3 examples. Remember?
All right, so
Yeah. So don't always think that it's going to work. Sometimes it doesn't work, and that's the tough part because you want it to work. Eliminating. Speaking of rational functions, common factors from 0 denominators. We have other options. There, yeah. If the denominator equals 0, canceling common factors in the numerator and denominator may reduce the fraction so a limit may exist.
that's why you factor before you find the answer. So,
Right. But you first have to figure it out is to see if it's 0.
right.
If it is, then try it, then factor it by removing the 0. Because if you factor something out and cancel it, what you're doing is you're eliminating the 0 part of it.
what is it, so by, doing what, zero?
by removing the zero. When you cancel all these things, you're removing the zero. Okay, here's an example here. Again, as I said, is the calculus is the first part. Then once you do that, the rest of it is all algebra. What's our asymptote here?
So the factor first. Well, we can see what the asymptote is.
We can't put zero in there.
Right.
Is there another number we can't put in there? One. If we put -1 in there, it'll be 1 + 1. That's okay. But we can't put, so x cannot equal 1 or x cannot equal 0. Now we got a problem. That's how come there's a huge gap here. This one, the asymptotic function is it's going to 0, but there's an opening right there. There's an open circle right there.
So it's not continuous.
No, but we're going to see if, since it is not continuous, right? We're going to see, does the limit exist?
Right.
Does the limit exist as we're getting close to 1 from both sides? So we'll look at, does, as x approaches 1, what do we get? So we get 1 squared plus 1 minus 2, 1 squared minus 1, 2 minus 2, 1 minus 1. So we get 0 over 0. That's the sign we're looking for, 0 over 0. So that tells us we should be able to factor something out. Since the second sign's a minus, the signs have to be different. And the bigger number has to be a plus. So what times what equals 2? When you subtract them, you get 1. 2 times 1 is 2, 2 minus 1 is 1, right?
X plus 2, x minus 1.
Right. And on the bottom, they both have an x.
That's the difference.
No, that was not squared.
Oh, x.
Let's just factor out a common term. So we're saying the limit exists and it's 3. As x approaches 1, right? So in other words, this limit here exists and it equals to 3. That's my L. But is the limit going to be, can we do the same thing going to 0?
If we set x approaches 0.
Yes.
The limit as x approaches.
Because remember, we're looking, our C values are the ones that give us trouble in the equation. X cannot equal 1, x cannot equal 0. We just fixed this one.
Because x is,
Well, yeah, because if we factor the same thing, we get 0 over 0. Now we wouldn't get 0 over 0. What we'd get is 2 over 0, negative 2 over 0. And because it's not 0 over 0, we can't go any further. It's going to be undefined. So that's why 0 over 0 is the magic number to factor out. Look at the graph. Did we see this graph before when we talked about no limits? If they go opposite directions, this one goes to positive infinity, this one negative infinity. So there's no limit.
so we can just tell that by the graph.
By the graph, yeah. And that's right here. We say something about the graph. If it's approaching this way, this way here, we know the limit exists and it's going to be 3. Is there another example sheet? Let me see. Yes. Okie doke. Do that one. So what's going to be our C value? Because if we put 0 in there, 0, the square root of 100 is 10. 10 minus 10 is 0 over 0. So that's our, so notice what we're looking at here is our limit is x approaches 0. X squared plus 100 minus 10 over x squared. Oop, no. So how do you think we're going to go about doing this one? How? We know so far it's good because we got 0 over 0. That means something can factor out.
We take.
Whenever you have something like this, your only thing you could really try is multiplying the top and bottom by the conjugate of the numerator.
Rationalizing the numerator.
Right. Oops, 100. That's usually the only thing you have you can try. So have at it. You want me to do it?
So 1 over the square root of x squared plus 100 plus 10.
Okay. What'd you get then? Work it out.
X plus 20.
No. That's what we have on top. So radical times radical, it's just whatever's inside there.
Supposed to. Negative.
So that's,
Positive.
and then that, so it's plus 10 radical x squared plus 100 minus 10 radical x squared plus 100 and then minus 100 all over, leave the bottom alone. These two cancel. So we have x squared plus 100 minus 100. The hundreds cancel. The x squares cancel. So we have 1 over square root of x squared plus 100 plus 10. Remember, this is the limit as x approaches 0. Zero plus 100. And plus 10.
Oh, okay. Yeah, I just didn't put the 0 in.
Right. This is it. I know you were there. One more step. Because a lot of times that's what whenever you do these things, make sure you put the limit in front of you. After you finish multiplying all together, you have to put that because that will remind you, take the limit as x approaches 0. We have one more rule to talk about, but this is one of the most complex ones, the sandwich theorem. And we only have like 15, 20 minutes left. So I'll save this one for next time. Because this is going to give us the sandwich theorem, also the squeeze theorem later on, is going to give us a rule that we're going to use throughout the rest of this course. It's pretty much finding, we'll be looking at sine x over x. When x goes to 0. So if we're looking at the limit as x approaches 0, what is sine of 0? But can you factor out sine? Yes, you can, knowing trigonometric, but we have to show you how this works. Because what the sandwich theorem says, if we can prove one theorem, one value, let's say it's f of x, and its limit exists, and we pick another value, g of x, and it also equals L, and this other one's between there. So if both, all of these, if this is below it and this is above it and they go to the same limit, what does this one have to go to? It has to go to L. And that's what it's proving. But it's a long drawn out process because it all depends on, first off, what functions do you pick on both sides? And then how do you apply them to come together? And that's why I don't want to spend no time. I want to go in depth in it because I want to make up some more examples as well.
So you have to use some identities.
We use that, yeah. Well, use identities. We use geometric ideas. I think it all depends on what you're given. If you're given trig functions, if you're given algebraic, or so it's how you manipulate it. Because with this one, we could find, because that's the same thing as square root of 1 minus cosine squared. That equals sine squared, or sine. Now at 0, we have cosine squared at 0 is 1, 1 minus 1, we still have 0, 0. What do we need to keep on doing? So it all depends on what we pick to both sides. So we have to pick something here, has to be, you have to pick something here. These two have to equal the same thing. And then we'll make this one equal the same thing as the limits exist. So that's what we'll do on Monday. So right now you have a lot of work to do on section 2.1. How many of y'all tried 2.1 already?
This one's not-
You started, okay.
I finished all of the problems except for the ones that involve the.
Okay, so that's in section 4 and 5, I believe.
Mhm.
Yeah, so do section 1 and section 2 over the weekend. And we'll do 3, 4, and 5 next week. Because 3 is gonna be the most difficult one. Not necessarily difficult, it's just gonna, that you're gonna hate me for. Because it deals with,
So that's the-
exactly, that's the hell week of calculus 1, because we're gonna look at the epsilon delta proof. And you'll hate yourself. You'll blame me.
So, we won't take intro first until after calculus 3.
In graduate school,
Well, I think, you're supposed to take intro first.
do we offer it here?
I don't think not your property.
I'm sorry, I don't remember seeing it. Yeah, it's after, because you have to understand proof of what. Because then you'll get into real analysis, and that's gonna help you define the rest of the mathematics.
Okay,